Bismillahirrahmanirrahim, and welcome back. Last time you would remember that last time we saw how we can use the Cartesian vector forms of vectors, of force vectors, to solve for equilibrium state in two-dimensional system. So this time we would formulate this setting in a more general context. Okay, so let's look at first a very trivial example. So here we have this particle, this small ball, and there are two forces acting on this ball. One is the unknown force F, and one of the forces 10 newtons. Okay, so now even this very simple example we can solve using the Cartesian vector form, even though we don't particularly need that form in this case. So how do we do that? So first of all, we recognize that all the forces are in x direction and there is no force in the y direction. So the sum of all the forces in x equals to 0. This implies that plus F plus 10 newtons equals to 0, because this force is also pointing in the positive x direction and this 10 newton force is also pointing in the positive x direction. And this is the only equation we need, because sum of all the forces in y equals to 0 is a very trivial equation, because there is no force in the y direction, as we can already see. So this is just to clarify some of the and reiterate some of the concepts. And now so we move to the general procedure of how we would analyze a system of co-planar forces to find the unknown forces. Okay, so just remember that right now we are still talking about only 2D systems. So we are not concerned with systems where we have forces in all the 3 dimensions. We would later do that in the next lecture hopefully, but for now we only consider system of forces where all the forces are in a plane. Okay, so first, what is the first step? First of all, we draw the free body diagram of whatever the object we are trying to analyze. Okay, like we saw before, what are the steps of drawing a free body diagram? We draw the outline, and then we draw the known and the unknown forces, and the next step we want to do is we would choose an appropriate axis. Okay, because now we want to use the Cartesian vector forms. It is very important that we are able to choose some suitable axes for our system. And like before in the free body diagram, we label all the forces, and then we choose a positive direction for all of our forces. Okay, so we have to make some kind of a guess for the forces, that what these forces are going to be in which direction. Okay, either it's going to be in the positive x direction or the negative x direction, and later we'll see that this guess doesn't really matter for our analysis at the end, but we have to assume some direction in the beginning. Okay, so the next step is that we solve for the two equations of equilibrium. For a two-dimensional system, the only two equations of equilibrium are sum of all the forces of x in x are equal to 0 and sum of all the forces in y equals to 0, as shown here. Okay, and so at the end of the day, these two equations we would be able to solve these two equations like two simultaneous equations, and we would have some unknown forces. Okay, so once we solve for the forces, then we can say that if the force component comes out to be positive, that means that our initial guess was correct and the force is actually in the direction that we assumed it to be. But if the force magnitude comes out to be negative, that just implies that our initial guess was not correct and the actual force is in the opposite direction. Okay, and like we discussed before, anytime we have a spring in our system, we would just assume that spring to be it obeys the Hooke's law, which means that force on the spring is equal to the spring constant times the extension. Okay, as given in the formula here. Okay, as we discussed before, any force that turns out to be negative, we reverse the direction that we initially assumed. Okay, so this is the procedure of analysis. We would apply this procedure on a few examples to get a clear picture of what we are talking about. Okay, so here we have a very simple example. It is from the book, that determine the tension in cables BA and BC necessary to support a 60 kilogram cylinder in figure 3.6a. This figure is given below. And now what we have here is that we have a load which is 60 kilograms, and there are two strings. One of the string is at an angle of 45 degrees, the other one is at the given through this similar triangle as we discussed before. And now we want to solve for these three forces. So what was our first step? So the first step, as we discussed earlier, was to draw the free body diagram. Okay, so let's see. We want to draw the free body diagram of this ring here. Okay, because all the three forces are acting on this ring, the most appropriate free body diagram would be for this ring. Okay, so let's start. So first of all, we draw the outline of the ring. So here we have the outline of the ring, and then we draw all the forces acting on the ring. Okay, and so let me draw the forces with something like a red. And the first force is the force due to this mass here, and so this is going to be 600 Newton. Okay, notice that to be very exact, I should first draw a free body diagram of this block separately, and then the tension equals the weight, and then that same tension applies here. But we can skip that step, and we can just say that the force here is the same as the weight here. Okay, the second force is going to be in this direction, and let's just call it FC. Okay, because this is acting towards the this point C. Again, the name is pretty arbitrary. You can choose whatever name you like, but this is one naming system that I like. Okay, the second force is in the other direction, and again we draw the similar triangle here. So this is 5, 3 and 4. Okay, so now I have drawn the free body diagram. Okay, so I have to label this force also, so I call this FB. Okay, so these are all the three forces acting on this ring. The next step, as we saw earlier, is to let me just reduce the size. Okay, and now I want to draw an axis. Okay, the most obvious choice for an axis is to simply draw the axis like this. So this is my x-axis and this is my y-axis. Okay, and I am assuming that my positive axis is in this direction, the positive y is in this direction. Again, this is a pretty arbitrary choice. I can choose any type of axis that I like, but of course this is the most common choice that most people make, and this is the most common choice that most of us we would be making. Okay, so the next step is to apply the equations of equilibrium. So the first equation is that sum of all the forces in x equals to 0. So how many forces do we have in x? We have a x component of the force Fc, and we have an x component of the force Fb. So Fc times cos of 45, this is the x component of the force Fc. Again, because I am not putting an arrow here, this means that this is a magnitude. Okay, and the second force is going to be in the negative direction, because this force is the x component of this force is in the negative direction. So, and because this is going to be a cos of theta, and which is equal to 4 over 5, and this equals to 0. So this is our first equation. Let me just correct my equal sign. Okay, So the second equation is the equation in the y-axis, and in the y-axis we have three forces, the y component of Fc, the y component of Fp, and this force is also in the y direction. So now for we say Fc sine of 45 degrees plus Fb times 3/5, and so now this is in the minus direction, so I would say minus 600 equals 0. Okay, so here we have these two simultaneous equations. So these are two simultaneous equations, and there are two unknowns. Okay, so two simultaneous equations with two unknowns. We already know how to solve them. You might have learned how to solve them in your maybe 7th or 8th grade. So I hope you can find Fc and Fb given these equations. Okay, one of the easiest method is because sine of 45 degrees is equal to the cos of 45 degrees, so we can just subtract the two equations and then we just get an equation for Fp. Once we have solved for Fp, then we can plug it in one of these equations to find the value of Fc. Okay, so I hope this is pretty clear, nothing very fancy here. Okay, so now I think all the steps should have been very clear. First of all, we draw the free body diagram, then we choose an axis, and once we have done both of those things, then we apply the equations of equilibrium. Okay, so here is the two free body diagrams. Again, like I discussed before, that we have avoided making this free body diagram because we know that for a block in equilibrium which has only two forces, the two forces are going to be equal, which means that the weight of the block is going to be equal to the tension in the string, and that tension is going to be the same tension which comes out to be here. Okay, this is an extra step which we can avoid also. Okay, so here is the working. So we get similar equations like these. Again, in the book they are using the value of 9.81, the value of G, but for this course we would use the value to be 10 meter per second square, which means that some of our answers would be a little bit different from what we have in the book. Okay, so here is another example. We want to draw the free body diagram of the ring A and identify each of the force. Okay, now here we are not required to solve the free body diagram because we are just required to draw the free body diagram. Okay, so we want to draw the free body diagram of this ring. Okay, so let's see how do we do that. Let me try to draw a ring using the circle. Okay, so that's much better. Okay, so now we have this ring, and how many forces? Again, I would like to draw my forces with the red. Okay, and my downward force is the 500 Newton force, which is already given here, and then there are going to be two unknown forces. One of the force is going to be in this direction at an angle of 45 degrees, and this force is, I'll call it Fd because it is going towards D. Some people also use the term FDA, which means that this is a force towards D from A, but it's a choice that you can make. Okay, this third force is in this direction. Again, my forces, because I'm using a stylus, is these are not as straight as they should be, but I hope you understand that this force is a straight line. Okay, and this angle is again 30 degrees using because this angle is going to be equal to this angle. Okay, and I call this force as Fb. So here I have drawn the free body diagram of this ring A. I have identified all of the forces. Notice we do not need to define an axis just to draw a free body diagram. We need to define an axis to solve using the Cartesian vector form. Okay. Okay, moving on. Now this is write two equations for equilibrium. Sum of x forces in x are equal to 0 and sum of the forces in y are equal to 0. Here we are only concerned with writing the equations, okay, and we're not really concerned with solving them. Okay, so now we have these two axes. The tricky part in this problem is that the two axes are they are still perpendicular to each other, but they are making this funny they are not the usual vertical axis and horizontal axis. Okay, so let me just clarify a few things so that we are able to solve. Okay, we know that this angle is 90 degrees. Okay, I'm trying to draw a block here, and secondly we also know that this angle is equal to 90 degrees. Okay, so this is the only two information that, and the other angles are already given. So now first of all we would try to write the equation for sum of all the forces in x are equal to 0. Okay, so how many forces do we have? We have this force P, we have this force for 400 Newton, 300 Newton, and this force F. So what is the component of this 400 Newton force in the x direction? So let's say that sum of all the forces in x equals to, so this is 450 cos of 30 degrees. That is the first equation, first component of our equation. The second one is minus 300, actually plus, because the x component is plus, y component of this 300 force is negative. Okay, so 300, and then we have cosine of 40 degrees. Okay, so these are the two terms. Then we want to find the x component of this force P. So I can extrapolate the x-axis here, and so this angle again is going to be 30 degrees, which means that the x component of P is going to be negative. It is going to be in the opposite direction. So I say minus P, and then we say cos of 30 degrees. Okay, and so the last equation, the last force is this force F, and so this is making an angle of 20 degrees with this perpendicular. Okay, so now we have to figure out the angle that this means. So this angle is 90 degrees, which means that this angle is 60 degrees. Okay, and because this whole thing is 90 degrees, which means that this angle is 10 degrees. Okay, this is again very simple trigonometry. You would have been very familiar with this already. So this means that this force F makes an angle of 10 degrees with the y-axis, and it's because it is pointing in this direction, which means its x component is going to be positive. So its x component, let me choose a different color. So its x component is this, and its y component is this. Okay, so its x component is going to be positive, but its y component is going to be negative. So now the x component of this force F is going to be plus F, and now we have sine of 10 degrees again, because here we see that we are trying to measure this length. Okay, so this is the first equation. Let's go back and write the second one, and sum of all the forces in y is equal to, so the first force is going to be 450. This is just positive in y direction, so that is going to be 450 sine of 30 degrees. This force is going to be in the negative direction, y direction. So now this is going to be minus 300 sine of 40 degrees, and this is also in the negative direction, which means that is minus p sine of 30 degrees. And the last force, again this also has a negative component, which means minus f times cos of 10 degrees. Okay, let me just clarify that for you guys. Okay, so these are the two equations of motion. As the problem already states that we do not want to solve these equations, we just want to write these equations. And now once we have these equations, you can already see that it's not actually very difficult to solve them also. So they become an equation when I say that this is equal to 0 and this also equals to 0. I hope it's pretty clear, nothing very fancy here. Okay, so now so we have these two other examples that we would solve during the class timings. I hope the concepts are pretty clear at this point.